Okay, I'll wait a few seconds. People are late. We have barely 75 people in class. Where are the rest? So, what do you mean by the website is not working here in Kigali, Bruno? What's the issue? The meeting link was there. Okay, let me post the meeting link. TAs, can you please post the meeting link on Piazza? Could you please do that immediately? And Bruno, just let the folks in Kigali know that the meeting link is on Piazza. Okay, let me begin. So, good morning, everybody. This is the last in our series of lectures on convolutional neural networks. We're going to start again with a quick recap of backpropagation through a CNN, and then we'll look at some additional backpropagation rules that were not covered in the last class. We'll look at some modifications, transposition, scaling, rotation, deformation, invariance to other kinds of operations besides shift. We'll look at segmentation and localization, and a little bit of the history of convolutional neural networks, which hopefully will give us time to briefly mention a couple of very popular architectures, resonance and dense nets. So here is the story that we have so far. Shift invariant pattern classification tasks, such as does this picture contain a cat, or does this recording include the word hello, are best performed by scanning for the target pattern using CNNs or time delay neural networks. Now, these are shared parameter models because scanning with a model is the same as having a very large model with many sub networks which are all identical. And these can be trained using variations of backpropagation that account for this shared parameter structure. So when you train a CNN of this kind, a CNN typically has several convolutional and pooling layers. The output of the final of these layers is typically flattened and passed through an MLP or maybe just a simple softmax. And so when you want to train the network for training the convolution and pooling layers, you pass each training instance through the net. You compute a divergence between the output of the net and the desired output of the network, and then backpropagate derivatives going backwards through the network. We have regular backpropagation rules through the final MLP. The derivatives at the input to this MLP can be folded back into the maps, into the same shapes as the maps that were unrolled to provide and flattened to provide the input to the MLP. So now we have derivatives, divergence derivatives for every element of every one of the maps in the final layer. Those derivatives can be further backpropagated through the rest of the network. And that's where we need adjustments. So the adjustments we saw were for both convolutional layers and pooling layers. For convolutional layers, given the derivatives for the output activation maps in any layer, we had to figure out how to compute the derivatives with respect to the affine maps on which the activation was applied to get the activation map. Subsequently, we had to figure out how to compute the derivatives for the output of the previous layer from which these affine maps were computed, and also for the filters that were used to compute these maps. For the pooling layers, given the derivatives with respect to the output of the pooling layer, we had to figure out how to compute the derivative with respect to the input of the layer. So convolution layers, first, how do you compute derivatives for the affine maps from the derivatives for the activation map? We saw this. The convolution operation gives us many affine maps, one per filter. Then we apply an activation function element-wise to get the final activation maps. During backprop, you expect that you will have the derivatives for every element of every one of these activation maps. To propagate those derivatives backward, to obtain derivatives for these affine maps, we used a simple chain rule. So what was the chain rule? Anybody remember? How did we get this derivative from these guys, from the elements over here? How did we do that? Anybody remember this? Come on, guys, this was easy. Specific chain rule we used. Right, derivative of the activation times the exactly. So this was just this very simple operation here. You multiplied the derivative with respect to the activation element by the derivative of the activation function itself to get the derivatives for the affine, every element of every affine map. Easy. So the next question was, how do you get the derivatives for, again, you have the input channels to a convolution, and then we had a filter, and this filter gave us a single output affine map. And so the question was, given the derivatives for all the elements of this affine map, how did we compute the derivatives going backwards for all of these input channels and for the filter? So does anybody remember how we did that? How did we do this, guys? If you were in the last class, you might have seen some flashing pictures. So what was the process, roughly speaking? Anyone? Do you remember how we did this? Come on, guys. You were there in the class, right? So how did we do that? Wait a few seconds. We redid the convolutions. What did we convolve? For the input pad, the derivative map and convolve with flipped weights. So, and for the filters, what did we do, Vimana? What did we do for the filters? You remember? For the filters, convolve the input and dl over dz. Fantastic, right? So that's all we did. If you want the derivatives for the y, the input channels, the derivative for any specific input channel was obtained by pulling out the corresponding channels of all the filters. And then, so these are the channels of all the filters. We flip these channels left to right, top to bottom, and then we zero padded these guys, all of these guys, right? And then we convolve the zero padded output derivative maps, affine derivative maps, with this transposed filter, left flipped filter, right? And that gave us the derivative for the input channel. So everybody remember this? Does everyone remember this? Yes or no? Right. This is easy, right? Nothing complex. And how did we compute the derivatives for the filter? So if this was an affine map obtained by using this filter against all of these input channels, then going backwards, we would have obtained the derivatives for all the elements of this affine map. We simply convolved this derivative map with all of these input channels to get the derivatives for all the elements of all the channels of the filter that was used to compute this affine map. Does everyone remember this? Yes or no? Okay. So, okay, I have a few thumbs up, so I'll just go with it. And so we've seen how to compute derivatives for these z's, for the filters, and for the input channels in the convolution layer. The other one was for the pooling layer. How do we compute derivatives for the pooling layer? Now, in the pooling layer, if you're performing max pooling basically pools groups of values to reduce jitter sensitivity. And so you have a pooling filter, which performs this grouping operation. And you scan the input with this pooling filter. The most common pooling is max pooling. which picks the largest element of every window that it's considering at every position. So if this were the window, again, what I mean by jitter sensitivity, we said that if you're looking for something like a flower, you can't get too specific that the petal must be, let me change the color, right? You can't get too specific and say that the petal must be exactly here, and this guy must be exactly here, and this guy must be exactly here for this to be a desired feature. If this thing moves left or right by a little bit, it still is the same feature. And so the way we got that was through this pooling filter, which looked at a little window over which this kind of jitter was considered permissible. And we picked the largest or the average or some other operation on all of these to achieve that jitter sensitivity. That answer your question, Vimana? Right. And so when you perform max pooling, you'd be looking at a window like this one and just pick the largest value. But the actual operation you performed was to first identify the location of the max and then copy that element over. So we just do that at every position through the input. When we were going backwards, now back propagation would give you the derivative for this element. This element was obtained from this window, but specifically this element was copied only the largest value over. So we know that the rest of them did not influence this element at all. So they get zero derivatives, and the derivative over here just gets copied going back into this position. So everybody remember this one? Does everyone remember this? Yes, no? Okay, like 10, I guess. I'm not too ambitious today. And so this was what the forward pass of max pooling was. You scan the input with a small window. Within each window, you pick the position of the largest value, and then you copied the input value at this position to the output. When you're going backwards, you have the location of the largest value. So you just copy the derivative over to the position from which it was obtained. The plus equals, why did we have the plus equals again over here instead of just an equals? Why do we have the plus equals? Anybody? Why do we have this here? Come on, you answered me 2 days ago. So Mac, the overlap, the same adjacent windows could pull the same large value. Now this, it turns out, is kind of an interesting thing. If you look at older versions of PyTorch, it didn't use plus equals, it just used equals. That was a bug. And so more recently they fixed it, and now they actually have plus equals, I believe, in the backdrop for max pooling, right? It doesn't really matter if adjacent windows don't overlap, but if they do, it matters. And then for mean pooling, we did the same thing, except that we computed the mean of all of these values and copied it over. So when you go back, the derivative at the location that this mean was copied into is now uniformly distributed over all the locations that contributed to it. So if it came from a 2x2 window, every element was multiplied by 1/4 and then added up to give you this guy. That's the mean, right? So the derivative was distributed in four equal parts over all of these 4 entries. In general, if the window is size k cross k, then the derivative is distributed over all 1/k, equally over all 1/k squared elements. And so here is the pseudocode for mean pooling. Going forward, you pick the mean value within each window. Going backwards, you already have the derivative out here. That gets copied after being weighted over by 1/k squared over all of those positions. And again, this plus equals accounts for the fact that adjacent windows might overlap. So is all of this clear to you guys? Everything that we've done so far? Right. So what will be the effect if you don't have a plus equals, Bruno? Then the derivative is going to be wrong. As you scan, you're just going to get the derivative from the latest window that contributed to it. So you're always going to have a derivative that's going to be off by a bit. That answer your question, Bruno? Okay. And so we've got both of these. And that leads us to our first poll because that is the end of our revision section. Then we go on to newer topics. So, Nelia, if you have ties, then both elements, when perturbed, will affect the output. So both of them will have uh, the derivative will get copied to both elements. Yes, very in most cases when you have max pooling, the pooling is done so that you don't have overlap. Not always, but in all the earlier models, that's how it was right? So if you're backdropping to the first index, if there's no overlap, that should be fine. If there is an overlap, that's about right. So I'm going to stop this poll. Can anybody answer this first question, true or false? True. Second one, true or false? True. Okay. So when backpropagating through a max pooling layer, derivatives from the pooling output backpropagate only to the position of the largest input within the input window, pooling window for that output. When backpropagating through a mean pooling layer, derivatives are distributed uniformly over the entire pooling window for that output. So that's everything we've done so far. But then we had something else that we didn't consider in the last class. Resampling layers. Upsampling and downsampling layers can increase or decrease the size of the map, right? So upsampling followed by a convolution we saw can be viewed as convolution with a fractional stride. Convolution or pulling followed by downsampling can be viewed as convolution or pulling with a stride greater than 1. So how do we backpropagate through upsampling and downsampling layers? First, what is the downsampling layer? In the downsampling layer, if we wanted to downsample by a factor of s, then we basically shaded out, discarded s minus 1 of every s rows and s minus 1 rows of every s columns. So all of these guys shaded in black, they were ignored. Effectively, they were masked out, and the rest of the elements were copied to the output. So my question to you is this. If this is what I'm doing, then does this element here contribute anything to the output? Does this element? Okay. So what would the derivative of the loss with respect to this element be? 0, right? So very easy. Back. Now, going back again, does this element contribute to the output? Yes or no? What is the derivative of the loss with respect to this element? What is it? 1. It's going to be the same as the loss derivative over here, right? Because this element just got copied to the output, right? Yes or no? And so the derivative over here is just going to get copied into this location. That makes sense to everybody? Right? So, but for this, there's a simple rule. The rule is if I have some process and the input is some size, and then this process gives you some output from which I compute a scalar loss, the gradient of this loss with respect to the input of this process is going to be exactly the same size as the input itself. That rule making sense to all of you guys? If you have these many elements being involved in computing this loss, then every element over here, this loss has a derivative with respect to every one of these elements. So the derivative the gradient, not the derivative, but the gradient, which is the transpose, must be the same size as the input itself. That makes sense to everybody? Right. And so here's what we would do. We know that the derivative of the input to the downsampling layer should be the same size as the input itself. So the first thing we do is to allocate a map of the size of the input that went into downsampling. Subsequently, you know, we know all the elements that were masked out when the downsampling happened. So their derivatives, as we already saw, are just going to be zero, right? And now just the remaining elements, those were the ones that were copied over. And because they were copied over, these guys basically came here as is. And so the derivatives here are going to go back. Whatever perturbation of this guy changes the loss by, that's exactly how much perturbation of this guy is going to change the loss by. So the derivative over here simply gets copied over. Is this process for the derivative of downsampling making sense? Yes. Okay. What does this process look like? What does the process look like going backwards? Anyone? It's just upsampling, right? The derivative of downsampling is, repeat after me. What's the derivative of downsampling? Guys? Upsampling, right? I mean, it's not exactly upsampling because there's some issues with the boundaries. But if you ignore what's happening at the boundaries, it's upsampling, okay? Now, I have pseudocode for I'll skip it, right? What about the upsampling layer? In the upsampling layer, we introduced S-1 rows and S-1 columns of zeros between adjacent elements, right? Okay, so Bruno, you say not exactly. Why is it not exactly? Can you tell me? You're right, but can you tell me why it's not exactly? Bruno, for this guy? Not very clear to me. So here, see this final column? If I'm upsampling from here, going back, I have no idea that I should be adding this final column or this final row. Because whether I downsample this one or whether I downsampled this larger one, let me clear this picture. So if I downsampled this guy, which is just these, the output is going to be exactly the same as if I downsampled this guy, right? Yes or no? Yes or no, right? Yes. And so there's this fuzziness about the boundary. Other than the fuzziness about the boundary, it's exactly an upsampling layer. And so this fuzziness of about the boundary is resolved by keeping track of the size of the input to the downsampling layer. That's all. That clarify, guys? Right. So that would have to be, you'd always start from the top left. So that's always a convention, Adil. Okay? All right. Now, what about upsampling? In upsampling, you're introducing S-1 rows and S-1 rows and S-1 columns of zeros between adjacent rows and columns. So this is what happens, right? Now, tell me this. When I'm going backwards, back propagation is going to give me some derivative for this element, right? Is there any element over here which, when perturbed, will change this guy? Is there any element of the input that would have changed this element? No, right? These were just zeros that were arbitrarily introduced without referring to the rest of the inputs. So which means that this derivative is really not influenced by any element over here. This is not contributing going backwards. That makes sense to everybody? Yes or no? Right. And so when I back propagate, again, the same rule, right? The derivative of the input to the upsampling layer, the gradient of the input to the upsampling layer must have the same size as the input itself. So, Mateos, if you're using interpolation going forward, then you'd have to worry about things. But in upsampling, you don't. You just stick zero. So you expect the convolution to take care of the learned convolution to take care of the interpolation. That answer you? Right? Okay. So here, when I'm going backwards, I expect the derivative to be the same size as this guy, but I know all of these elements really have no counterpart in the input. They were just zeros that were introduced when you're going forward, right? So during backprop, these guys do not influence the derivatives going backwards, right? But what about this guy? What about this guy? What can we say about its derivative going back? Anyone? One? So this derivative, okay, this element is the same as this element, correct? Yes or no? Right? So what is this derivative? What is this derivative? It's going to be just copied over from here. Make sense to everybody? Right? And so you just copy those derivatives over. What does this operation look like? What does this operation look like? Downsampling, right? So the derivative of upsampling is a downsampling process. The derivative of downsampling is an upsampling process. The only fuzziness is about the boundaries. If you keep track of the sizes of the inputs going forward, you always know how to deal with the boundaries, okay? And so writing code for back propagating through downsampling or upsampling is really, really simple, right? You're literally just copying things over in the right locations. Now, in reality, when you actually perform downsampling after an operation, you don't actually directly perform the full operation and then perform downsampling. That would be a lot of unnecessary computation. So what you do is you just perform the operation. Event, what is that? These zeros, they only used further downstream, right, Yvette? You introduce zeros, you increase the size of the input, and then they're used further downstream. Correct? Yvette? Yeah. But they have not come from anything over here. So these derivatives are simply dropped. Right? So because they really don't have, there's nothing you can perturb over here that's going to change the zero. The zero was just zero stuck in, which means that this contributes nothing to the derivatives out here. That makes sense to everybody? I'm assuming so, right? So now, typically, you don't actually perform explicit downsampling. You're going to perform convolution or pooling with a stride. And when you perform convolution or pooling with a stride, then this is effectively performing convolution with downsampling. But there is an annoying bit about it. If I perform convolution with a stride, say doing this window and then stride by 2 and then doing this window and so on, and then you try to work out the back propagation rules, the math gets very ugly very quickly because you have to deal with the business of the stride. So it's much, much, much simpler to actually think of convolution with a stride as convolution with a stride of 1 followed by downsampling. Because we know exactly how to compute derivatives going backward through this guy. That's just another convolution operation. And we know exactly how to compute derivatives through this guy. That's just an upsampling operation. So rather than trying to compute derivatives directly over here for convolution with a stride of 2, there is the realization that it's a regular convolution with a stride of 1 followed by downsampling. And so backpropagation is first going to backpropagate through the downsampling and then through the convolution with a stride of 1. That makes sense to everybody? Yes, no? Rest of you guys? I'm seeing like half a dozen yeses. Okay. So, like 5 yeses, man. Can I have 10 today? I was asking for 25 yesterday. I was greedy. All right. Okay. All right. So, this is what you'd want to do. First, back propagate through the downsampling and then through the convolution with stride of 1. Convolution with a fractional stride. What exactly was convolution with a fractional stride? Anybody? What was that? What was convolution with a fractional stride? Upsampling followed by convolution, correct? So convolution, when I say convolution with a stride of 0.5, what you're really doing is upsampling by a factor of 2 and then convolving with a stride of 1. This is the equivalent of striding by half a pixel at a time, right? Because the stride, whatever the stride is, 1 over the stride, is the scale by which the output is modified. If the stride is 2, the output is going to shrink by a factor of 2. If the stride is 0.5, the output is going to expand by a factor of 2, right? So this is actually upsampling by 2 followed by a stride of 1, right? This, everybody good with this, Bruno? This makes sense to you? Since you had the question? Okay, so what is the doubt, Bruno? This guy, let's say I have something of this kind, right? If I stride by 1, assuming I have 0 padded to keep this, maintain the output is still going to be 2 cross 2, correct? Bruno? If I stride by 1. If I stride by 2, what is the size of the output going to be? It's just going to be 1 pixel. So it has shrunk by a factor of 2 on every side, right? Yes. So in general, striding by S decreases the size by factor S, correct? Yeah. What if S is less than 1? If S is 0.5, it's going to modify the size of the input by a factor 2, right? So if the input is size n, and then if you stride by S, the output is size n over S, correct? Yes or no? What if S is a fraction? Then what happens? If S is 0.5, what happens? It increases, right? So that's what a fractional stride means. But then how exactly do you implement it? The way you implement it is by upsampling by a factor 1 over S and then striding by 1. That makes sense to everybody? Right, so that's what a fractional convolving with a fractional stride is. Bruno, that answer your question? Okay. So when you encounter a convolutional layer with a fractional stride, you must realize that it's actually an upsampling followed by a regular convolution, right? And then you can just back propagate through the standard convolution rule, derivative rules for the convolution with stride 1, and the very simple rules we saw for back propagating through upsampling by 2. So this makes sense to everybody? Okay. So Mate was the boundaries. You have to keep track of sizes, that's all. So again, pooling is typically performed with strides greater than 1, results in shrinking of the map, right? And so again, when you're pooling with a stride, it's convenient to think of it as pooling with a stride 1 followed by downsampling. And same thing, right? So that's the math. But then it turns out, as I was saying yesterday, so Edward, what is preferred over what? I'm not sure what the two options are in your mind. Can you clarify? You can't. How do you stride by less than 1 when you're shifting forward? Can you stride by 0.5? I have a picture of this kind, right? I have a number, let's say. I have these guys. These are my pixels. And then I'm convolving by a 2 cross 2 filter, right? Can this stride by less than 1, Edward? Like less than 1? It cannot. This is the way you implement it, right? Because everything is integer. That's why. So even mathematically, you basically just upsample and convolve. Anyways, so go back to our point that it's always simpler when you look at it through code. Suppose I have a simple operation, right? Function y equals, so I have some function which says y equals f of x. Let me erase this. I'm writing some crappy pseudocode, but live with me, right? Function. And then within this code, I have z equals, and let me actually x and w, right? Z equals wx and y equals some sigma of z. Let's say if this is my code, right? Now I give you dl over dy. I want function dl over dx, comma dl over dw equals whatever the derivative of dl over dy. What is this function going to look like? Basically, this computed y from x and w. I want the reverse function which computes the derivatives of a loss with respect to x and w given the derivative of the loss with respect to y. What would this look like? Is this problem statement making sense to you guys? What I just asked. Maybe I can make it clearer, right? Let's say I'm given dl over dy, and so I want a function f. This is a function definition, and the output of the function is dl over dx and dl over dw, okay? And I want this derivative function whose input is dl over dy. What will this function look like? Can anybody tell me? Just writing this code from this code. Anyone? With a quick look? Here. So here's what happens. Y is a function of z, right? We have the derivative for y. So what is dl over dz? What is dl over dz? That's simply going to be dl over dy sigma prime, correct? Yes or no? Over here. Now I have dl over dz, right? What is dl over dw? What is this? What is this? That's going to be dl over dz times z, right? W. Or is it not? It's going to be dl over dz times y. X, sorry. X, right? And dl over dx is going to be dl over dz times w, right? This makes sense to everybody, what I just wrote? So look what I did. I didn't even worry about what the code was, right? I just saw the z equals wx, y equals sigma of z. So I started from the bottom and computed the derivative for z. Then I just took a step back and computed the derivative for w and x, right? Yes, no? Did you guys understand this? Right. It doesn't matter if this operation is in a loop. For I equals 1 to n, whatever, the same operation holds. And so here is what I would do. If I'm looking at what's happening inside a convolution, I'm scanning the input, right? Then within each input, I'm going over all the filters. I'm initializing the z value for it. The z is what, going forward, you're computing z's, right? And then you're computing y's. Then at each position, I'm going over the filter, right? And within the filter, I'm just adding the w times the y from the previous layer to z. So this operation finally gives me a z at every position. The y itself is just computed by applying an activation to it. So this code making sense to everybody? Bruno, this making sense? What we just did? Right. I'm going to use exactly the same rules that I did earlier, okay? I'm going to say, if I want to compute the derivatives, say I have the derivative for y. How do I compute the derivatives for z, w, and the y of the previous layer? I'm going to do the same thing. I'm going to, first, it's back propagation. So the order of all of these loops is going to be reversed, okay? Then just as I did in my example, first, I'm going to get the derivative for z from the derivative of y up here by multiplying the derivative for the activation function. And then within the innermost loop, again, z is obtained by multiplying w and y. So the derivative for y is the derivative for z times w, and the derivative for w is the derivative for z times y. Is this making sense? What I just did. Rest of you guys, this making sense, right? I'm using exactly the same code as here with exactly the same indices. I don't change a single thing. And so I don't even have to think about it. Everything will just work out because the arithmetic makes sense, right? H is the height, W is the width, you bet, of the input. This makes sense to everybody? Yes or no, guys? This makes sense. Rest of you guys. Can I see a dozen thumbs ups, please? 7, 8, 30. Okay, I got 13. Good number. And so that's all I need to do, right? I didn't need to understand that things were convolutions. I didn't need to understand a single thing. I literally just flipped the code around. And this works even if I'm convolving with a stride. Going forward, I'll be doing everything with a stride. Going backward, I'm even to use the same logic. All that I do is that I'm going to be going backwards. So this should have really been over here. It doesn't matter whether I'm going forward or backward. If I were doing this right, the order of the indices would be flipped, and the rest of the arithmetic is exactly the same. Where are you seeing, speaking of x minus, this is the position, right? So when you're scanning, you're going to, you're scanning within this window to perform the integration starting from this position. So one of these is this position, the other is the position within the window, Viman. That makes sense? When you're computing the z, right? Okay. So that's all it is, right? And so here we are. We can do the same thing, right? Pooling, you can do the same thing. So pooling, you can just flip things around and the whole thing just works, okay? I'll skip this. So that goes to our second point. The idea I was trying to convey was, if you don't understand the math, you can just look at the code and you can always write code to compute derivatives without knowing the first thing about what the math is doing. Simply by writing everything backwards. It's amazing. You can use this logic to compute derivatives of any function. It doesn't matter how ugly the function is. If you can write code for the function, you can compute derivatives for the function using the same code running backwards. Okay. I'll give you 5 seconds. Okay. I'll end the poll. Anybody want to answer these questions? True, true, false. True, true, true. 3 twos. Okay, let's see. Bruno was right. Right. The backward pass of an upsampling layer is downsampling. The backward pass of a downsampling layer is upsampling. You can't simply use an upsampling layer as the backward pass of downsampling and vice versa. Right? Why is that? Why is the third one false? Anybody? Why is the third one false? Guys? So those of you who answered false, you got it right. You need to account for the original shape of the input because of the craziness at the boundaries. If you ignore the boundaries, you could do so, but you have to worry about the boundaries, right? And so we've shown how to compute derivatives for every bit of this convolutional network, regardless of whether you have strides, what have you, correct? So is everybody comfortable that we've done all of this so far? Yes or no? Okay, fantastic. And so the story so far is that the convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, pooling layers that operate over groups of outputs from the convolution layer for jitter invariance, and resampling layers that can increase or decrease the spatial extent of the representation. These are often integrated with preceding or succeeding operations to convert them to operations with integer or fractional strides. The parameters of the network can be learned through regular backpropagation. Max pooling layers must propagate derivatives only over the maximum element for each pool. Other pooling operators use regular gradients or subgradients. Derivatives must sum over appropriate sets of elements to account for the fact that the network is in fact a shared parameter network. So jitter invariance, where again, we went over this a little while about Yvette. I said that, if you had a filter that detected this feature, you still wanted to say you had that this pattern from a flower was seen, even if this petal moved forward by half a pixel, or if this one moved left by a pixel, right? And so you wanted invariance or in the positional invariance in the components that compose the larger pattern. And that came through max pooling. That answer you, Yvette? So, right. CNNs are shift invariant, meaning we said where we exactly, Umana, right? So we started off saying we want the network to fire regardless of the location of the flower. So we created this entire theory and a lot of pretty algorithms to construct and train networks that could detect, for instance, that both of these pictures have a flower. But what if so these are shift invariants, but what if we want other kinds of invariants? What if I want rotation invariance? I wanted to detect the flower even if the flower is rotated a little bit. I wanted to detect a flower even if the flower has scaled up or if it's reflected upside down. How could I introduce these invariances? Any idea? How could we? Augmentation? Augmentation's a good idea, but something more, yeah, augmentation is generally how we do it. But if you were to do it theoretically correctly, how would you do it? Depth, right? So here is what happened. When I was detecting a flower, what was it I actually did? I had a flower pattern detector and I scanned the input. And so the same flower pattern detector was applied in both locations in order for me to get position invariance, right? Yes or no? Yes or no, guys? Right. Okay. So I can think of shift invariance from a different perspective. I can write this as saying that when I'm scanning with a filter, instead I can say that I'm actually scanning with two filters. One is the original, I'm computing with two filters. One is the original filter, and the other is a shifted version of the same filter, right? And that's going to give me these two outputs. Yes or no? Right? So I got shift invariance by shifting the filter. Yes or no? That makes sense to you guys? What was scanning? It was just shifting the filter, right? I got shift invariance by shifting the filter. How would I get rotation invariance? Using the same theory. You'd allow the filter to rotate. How would I get scaling invariance? And allow the filter to scale, right? Very simple. The concept is so pretty. And so, if I want to generalize shift invariant, in the original thing, I said the z at a new position was a y convolved by a shifted version of the filter to position ij, right? If I want rotation invariance, I get a z which convolves the y with a rotated version of the filter. I can combine rotation and shift and say rotate and shift. And so I can now I'm going to get rotation invariance for the same feature. This makes sense to everybody? Yes, no? Right, beautiful, right? So there's a problem. Why don't we do this? Why don't we do this? It has to do with the fact that you're going to have, you know, you can, it's not just rotation. You can think of every kind of transform that you want invariance to. And so you're going to transform this filter to explicitly make copies of the filter with each transformation applied to the filter. And then you'd be scanning with all of these transformed versions of the filter, right? This means we need the set of transforms to be enumerated and discrete. So I'd have a discrete because I'm making copies of the filter, right? So I need a discrete set of rotations, scaling, reflections, etc. that I can list out, and this filter is going to be put through all of these guys. And the code itself is, here was a standard code. You were scanning. At each position, you pulled out a chunk of the input. You did a tensor product with the filters and then applied an activation. Here, at each position, you're going to pull out a chunk of the input, but then the filter itself, you have an additional loop. These are all the transforms that you're going to apply to the filter. And so the chunk is going to be convolved with all the transformed versions of the filter, which means the set of permitted transforms has to be in this code. It has to be enumerated. And how many transforms can you get? If I want rotation invariance, I have rotation by 1 degree, rotation by 2 degrees, rotation by 3 degrees, rotation by 270 degrees, right? This is going to be an enormous number, and every one of them is going to create an output map. That makes sense to every one of you guys? Right? So each one of these is going to create a map, right? And the whole thing is just going to blow up. That's why we don't do it. That's why we just simply use augmentation, and 270 was a random number I chose. You can have, you can have any number of degrees, right? So, but it's exact, unlike when you're using augmentation, because you do this when you're back propagating. If you back propagate through all of these variants of all the channels computed by all the variants of the filter, you're going to get the derivatives for all of these variants of the filter. Those derivatives can all be transformed back, and you're going to get the derivative for the original base filter itself. And that's what you would use. And the nice thing about this is that it's not just rotations, it's not just reflections, it's not just any one of these. You can have any kind of distortion, any kind of transformation of the filters, and you can choose the kind of distortions you want invariance to, and you can build your network, or you can transform your filters through those distortions and make the network invariant to it. Unfortunately, it's computationally ridiculous, and so we never do it. We take the much simpler method of simply augmenting our data. That makes sense to everybody? Yes, no? What we just said? Right. But the idea is beautiful, isn't it? Don't you think? What do you think? Right. If that made sense, give me a yes. If you think the idea is beautiful, give me some other. Uh, all right. Anyways, let me move on. Right. So the story so far, I can add this new bullet. The models can be easily modified to include invariance to other transforms, although these tend to be computationally absurd. Okay. What about the location? We said We want to build a network that will fire regardless of the location of the flower. But that we obtain by effectively scanning for the flower. And so if it fired at any location in the picture, it means there was a flower. But then could we not look at where it fired and also detect where the flower occurred? What do you guys think? What do you guys think? Right? We were scanning. And if it fired at any location, we said there was a flower. But then you can say, hey, you know what? It was high here and here. So I think the flowers are here and here. You should be able to say that, right? Yes, if we keep track. Not quite, because once you begin distributing the patterns, things get a little ugly. But then there are many situations where we really want to know where the pattern was detected. So we know that this guy actually carries information about the location of the flower somewhere in it. So what is done when you're trying to find the locations, we try to detect bounding boxes, basically the box within which the pattern has occurred. And now you have what is called a multitask network, which generates two outputs. The first, of course, is your regular class output. The second is a network, is a head, which gives you the coordinates of the bounding box within which the object was detected. And now the network, you're going to have training data, which not only tells you where, if there is a flower, but where the flower was. And the location information in the training data is now going to be used to train the second head. This makes sense to everybody? Yes, no? Yeah. And so you can do this to detect other kinds of things. You might have seen these networks which draw skeletons of this kind, right? The joints of a stick model. That uses the same technique. In fact, if you had been in CMU 5 years ago, as you walk down the corridor from the Gates building to the Hillman building, there was a screen at the end, and Yasser Sheikh had put up this demo, which would draw the skeleton. It was very scary, of every person walking down the corridor. So you could see your own skeleton. He did that with a CNN, which basically just implemented this. He had the best model for this in the world. So you can use this for pose estimation and whatnot, right? So uh, here is the third point. Fifteen seconds, guys. Okay. I'm going to end this poll shortly. Hurry up and click. Otherwise, there she goes. Okay. Anybody want to tell me the answer to the questions? True, true, true. Are you sure? Let's see. True, true, true. Indeed, you're right? To find the position using a CNN, we need multiple output layers after the final convolution. One to identify the class, the other to predict the position of the object. CNNs are invariant to the position, but not the orientation or scale of the target pattern. To make them invariant to a transform versions of every filter must be included in the model for every transform considered. Alternately, you can just use augmentation of the data, where you include every variant of the that you want robustness to in the training data. So there are many variants to this model. You can have very deep networks, 100 or more layers. This typically uses a formalism called ResNet. David, yes, if you were pedantic, must is the wrong answer, is the wrong word. Okay. If you want to have many, many layers in the network, turns out training them is hard. So we use a formalism called ResNets, which you will encounter in your homework. You have this thing called depth-wise convolutions, which are another variant of parameter sharing, and they're used very often when you want to train a very small model, which is just as almost as effective as a full model. Here, instead of using multiple independent filters with independent parameters, we use common layer-wise weights and combine the layers differently for each filter. So what exactly do I mean by this? Now think of this. In your standard convolution, if I have a filter of this kind, the filter has as many channels as the number of input channels. Yes or no? Right? What do you guys think? Okay. So what really happens? One way of thinking about it is that the first channel of the filter convolves the first channel of the input. The second channel of the filter convolves the second channel of the input, right? The third channel of the filter convolves the third channel of the input, and so on, right? And so the output of this is going to be one channel, each of which is being obtained by convolving one of the channels of the filter with the corresponding input channel. Then all of these are just summed up to get the final output. This is the actual operation we're performing, right? Yes or no? Right. Makes sense to everybody? The fact that we just wrote big fat summations doesn't change the fact that this is what we really do, right? So if it makes sense, give me thumbs up. I'd like to wait to see 10 or 15 because this formalism pops up. Okay, I got my 15. So if I have 3 filters, how much computation am I performing? Each of these filters has as many channels as the input. Each channel of each filter is convolving the corresponding input channel. So if I had 3 filters and if there were 10 input channels, I'm actually performing 30 convolutions, which are being collapsed to 3 output channels. This making sense? The numbers that I just gave you? If I have 3 filters and each of them has 10 channels, which means there are 10 input channels, so I'm computing 30 of these planes, which are being collapsed into 3 outputs. That's a lot of computation because I'm performing 30 convolutions, right? And I'm computing a lot of intermediate values. So depth-wise convolution cheats a bit. What it does, it says, instead of having each of these filters, each channel of every filter is different, right? Instead, I'm going to have one filter and I convolve the input with this filter. The convolution is going to give me as many channels as the number of channels in the filter or the input. In your traditional convolution, you just collapse these and you get one output, right? Here, instead of collapsing them and getting one output, I do a weighted sum of these guys. And by changing the weights with which these guys are added, I get different output channels. That makes sense to everybody? All of you guys, yes, no? Right? And so, with just one set of convolutions, I got multiple output channels. This was what was called a depth-wise convolution. If this made sense, give me a thumbs up. I have 2 thumbs ups, right? Today I like the number 15, so yeah, 15. Exactly, right? This has far fewer parameters. It computes far fewer intermediate values. So obviously it's not going to be as good as a full convolution, but it gets most of the way there and for a fraction of the compute and a fraction of the memory and a fraction of the number of parameters, right? This makes sense. If you collapse the input channels, you're going to get only one input channel, right? And so the number of parameters is going to be 1. If you collapse the input channel, you're just left with one of these planes for each output. So the number of parameters is going to be far fewer. That's a good question, Bruno. It's just that it's going to be suboptimal, right? You don't have enough flexibility with doing that because the input is collapsed. So conventional versus depth-wise. In conventional convolution, each of these filters is going to give you an output channel, right? And then they're all summed up. In depth-wise, These filter channels give you a different output channels, and we just sum them up with different weights to get the different output channels. And so the number of parameters and the number of computations and the number of intermediate values are all going to be far fewer. I have some arithmetic here. Let's skip that. I think you guys got the idea. So here is my final poll. Fifteen seconds, guys. 5. Okay. Let me end this. Did anybody notice these pictures on the top right? Okay. There's a code over there. I'll let you figure out what the code was. I had one on every poll. What are the answers? False and true, right? Filters and depth-wise convolutions convolve all the input channels simultaneously and sum the result. No, they actually keep this channel separately and then do a different weighted sum for each output. They require far fewer parameters and computation than regular convolutions. Right. So depth-wise convolutions, because you're not collapsing it and you're retaining the depth of input channels, they call it depth-wise convolutions. So to add to our lessons, several variations of the basic model exist to obtain greater parameter efficiency, better ability to compute derivatives, etc. Right? This is the last bullet. What do the filters themselves learn? Now, again, going back to our second lesson on convolutional networks, there was a notion of a receptive field, which was the region of the input that each filter saw. But it also refers to the patterns that it detects. The pattern in the input image that each neuron sees is, it's a receptive pattern, receptive field, right? The receptive field for first layer neurons is simply the arrangement of weights. For higher layer neurons, because the higher layer neurons can respond to different groups of different combinations of first layer patterns, you actually need to use backpropagation to detect what the neuron has fired for, and this is going to be input specific. And so there's a process to it. I won't get into the details, but here are what we find. So here as a CNN, these are CNNs that were trained on different classes. And so when you analyze the CNN and see what the receptive field was, what patterns the neurons fired for in response to, for each of these classes, you find that the first layer neurons, they all end up detecting these patterns. What do these guys look like? The patterns, the receptive fields of the first layer pattern neurons, what do they look like? Edges? Do they look familiar to something we saw earlier, a few lectures ago? Like what, Ayush? S cells. These end up looking much like the kinds of patterns that the mammalian vision system captures. That's the magic. You put in all of this thing, it was kind of started off as a mimicry of mammalian vision. And guess what? When you train the model, the kinds of patterns it detects at the lowest level indeed look like the kind of patterns that our visual cortex seems to respond to. That's magic, isn't it? I don't know about you, right? And then look at what the higher level cells get. When they're looking at faces, the higher level neurons, intermediate neurons get all parts of faces. The highest level neurons each fire for a different kind of face in a slightly different position, right? When you're looking at cars, the intermediate neurons get parts of cars. The highest level, they find cars in different positions. Elephants, these find intermediate neurons fire for parts of elephants. The highest level neurons fire for full elephants in different positions. Same with chairs, right? And so what we are finding is that you actually get this very hierarchical buildup of patterns, very satisfying, which is exactly the kind of thing we even see in mammalian vision, and we hope to get, and we indeed do get it, right? There are lots of training issues, standard convergence issues. The solution is to use ADAM or other momentum style algorithms, tricks like batch norm. You'll do those in your homework. The number of parameters can quickly become very large, so you'll get insufficient training data to train the model well. Solution: data augmentation. What we do is that we modify our training data to make fake training instances. For example, this guy is some kind of a crazy cell, but if I rotate it a bit to the right, it remains exactly the same class. If I flip it, it remains the same class. So we modify the data through things like rotation, translation, rescaling, flipping, shearing a bit, stretching, to create different variants of the same data instance, which will have the same class label. And these augmented data are often used to expand your training data. CNNs are one of the most frequently used NNet formalisms today, used everywhere, not just for images. They're used in speech and audio processing, and they're even used in text processing, amazingly enough, right? So, and if you actually go to Andre Karpathy's Stanford webpage, you can get some very nice visual examples. So let's just spend a little time going through the history. The first really viable CNN was Jan LeCun's LeNet. And Jan LeCun's LeNet, this was it. This was from, I think, the original paper. An image would go in, which was a 32 cross 32 pixel image. The first layer consisted of 4 5 cross 5 convolutional filters. So the first layer would give you 4 maps. And because these were 5 cross 5, the result was only 28 cross 28. Remember, the edges, you lose things at the edges. Then he had a max pooling layer which looked at 2 cross 2 windows and then had a stride of 2. So it shrank everything by a factor of 2. And that resulted in 5 14 cross 14 maps. 4. Then he had 10 filters, each of size 5 cross 5. And so as a result, because the filters are size 5 cross 5, you're going to lose 4 rows and 4 columns. And the outputs were, there's 10, 4, 8, actually 12. The outputs were 12 10 cross 10 maps. Then again, max pooling with a stride of 2 brought it down to 5 cross 5. These were flattened and just put through an NLP. This was a very simple model, and this basically revolutionized machine learning, right? So this was LeNet 6, is it? Maybe I got the numbers wrong, but all the details of the original LeNet are on the slide. Now, LeNet happened in the late 80s, and then things didn't move a lot for a very long time till 2012, when Hinton and co. showed that COMNets are really good at image classification. There's this classic challenge called ImageNet, the large-scale visual recognition challenge, where the actual data set had millions of images and thousands of categories. The standard evaluation used 1.2 million pictures, thousands of categories. There were all of these different categories, right? Different examples. And before CNNs were used, the best models of the day, I think, gave us something like a 25% accuracy in top 5 accuracy in the best case. And they couldn't get past it. Then Hinton and co came up with this thing called AlexNet. It was so large for that day that it wouldn't fit on one GPU, so they had to fit it in 2. And the picture wouldn't fit in the paper, so they had to crop the picture. This is the original picture from the paper. The upper portion of the picture is cropped. The network contained 60 million parameters and 650,000 neurons. And they introduced a few interesting variants. This was the first time that they actually used ReLU activations in a convolutional network. And so again, these are all the details of the network. I'll skip the details. For the total parameters, they had 650K neurons, 60 million parameters, 630 million connections. This was considered enormous for the day. And then during testing, They would take each test image and crop it in many different ways, in 10 different ways, and classify each crop and then vote over the lot. And some more training details. But here's the bottom line. Overnight, the error that was 25% went down from 25 to 18.2 with a single ConNet. Even better, when they trained 7 different networks and voted over all 7, the error went down to 15.4%. So there was a 40% reduction in the error overnight when they started using ConNets. This was the moment when people realized that neural networks actually work, and this changed the world, right? Of course, they found more things on their network. They looked at the patterns that the neurons at different layers responded to. Sure enough, the first layer neurons end up looking like S cells. In mammalian vision, they detect these oriented edges, very beautiful. Furthermore, they found that the network learns very useful representations. So, first, here are some classifications. This was a mite, it classifies it as a mite. It's a container ship, classifies it as a container ship, motor scooter, leopard. It does make errors, but the errors are reasonable. This is supposed to be a grill, according to ImageNet. The model recognized it as a convertible. Hey, it seems right, right? This is supposed to be a cherry. The model thought it was a Dalmatian. I think I kind of agree with the model though, more than the label and the data set, right? So this was supposed to be a mushroom, but the model recognized agaric, which is down here, and so on, right? This is supposed to be a Madagascar cat. It thought it was a squirrel monkey. It looks like a squirrel monkey. So even the errors were very reasonable. And here was something more important that really mattered. In the final layer of the network, just before classification, you get a feature that is put through the softmax, right? They use that feature as a representation for the input and performed retrieval. And so when they use a feature derived from a picture of this flower and they retrieve other images from the data set, they retrieve flowers. When they use an example of an elephant, the other images that they retrieve are elephants. For a ship, they're ships. For this Halloween lantern, all the other images they retrieved were also Halloween lanterns. So they showed that the network actually learns semantically meaningful features of the data, which is pretty amazing, right? Of course, once somebody jumps into the fray, others jump in, start something off, others jump into the fray as well. So Zeiler and Fergus trained a small variant on AlexNet and they reduced the error from 15.4 to 14.8. Then these guys, the VGGNet guys, they ran an insane number of experiments with 140 million parameters, which was considered too large for the day, and brought the error down to 7.3%. Then Google doesn't want to be left behind, so they came up with this really ugly model, which they call Inception. It brought it down to 6.7%, all within a year, right? And then ResNet came in, and they chopped that error down to 3.5%. And so here we are, right? Within 1 year, we've gone from a couple of years, we've gone from a 25% error to a 3.5% error. Why ugly? It looks ugly to me. I don't know about you guys, but this looks hideous. Okay, so all right. And so ResNet you're going to encounter ResNet. So I'll skip that, right? Then people came up with DenseNet, and then it became some kind of a crazy competition where you could literally go out for a cup of coffee and come back and find an improvement in the error rate. It was that bad. Then eventually people cooled down and then they moved on to more interesting things. Convolutional neural networks had conquered the world. And of course, there are thousands of papers, hundreds of applications, CNNs for speech recognition, language processing, what have you, and CNN for your homework, right? I have some more examples on the slides. I'll skip that. End of the class at 7:49. Did the lecture make sense? Give me a thumbs up if it did. Can I wait for like 40 thumbs ups this time because it's the end of the class? Yeah. Certainly. Okay. All right, guys. Do you have any questions? If I'll stop the recording. Do you have any questions?
Professor, I have a